Hello everyone and welcome to the CAC and ME guys. So today we will cover the thermal stresses in a material or a bar or a block due to the change in temperature. So first of I am taking an example of there is a one bar which is fixed between the two rigid supports. And due to the change in temperature from temperature T1 to T2 there is a change in stresses, change in dimension, and due to this stresses will produce. Here we can see that the initial length of the bar is L and there is a fixed rigid support which is fixed between the two rigid supports, but there is a change in temperature, so it wants to expand, but due to the rigid support or the wall it will not change its length. Due to this the stresses will develop, which is called as the stresses due to the thermal load or due to the change in temperature, which is termed as the thermal stresses. So this is the basic concept behind the stresses or thermal stresses. Now we are taking the example of the rectangular block. Here the case number 1. Here I am taking an example of the free expansion. Case number 1, free expansion of a rectangular block. Here one is the rectangular block and there is a free to expand, just like that it is the surface and the block is resting on it. There is no obstruction on the other faces, so it can be freely expand to the X, Y and the Z direction. So it is the case of the free expansion. So change in length is given by the L1 minus L is equals to delta thermal in the X direction is equals to alpha TL. The del V is given by the alpha T B change in its width. Del T is given by the alpha T into small t. Here T is the thickness. Here T is in the degrees centigrade, which is showing the temperature difference. It is showing temperature difference, and the alpha is the coefficient of thermal expansion. Coefficient of thermal expansion. So from here we can see that the thermal stresses in the change in the thermal strain in the X direction is greater than the thermal strain in the Z direction is greater than the thermal strain in the Y direction. Only in case of the cube all of the three stresses will be equal, only in case of the cube. So thermal strain can be thermal strain in the X direction is given by the change in length in the X direction due to the thermal temperature change or thermal load divided by original length, which is equals to alpha T L upon L, which is given by the alpha T. The thermal strain is the in the three mutual perpendicular direction are equal and like in nature. So sigma thermal X is equals to sigma thermal in Y direction. Stresses in thermal stresses in Z direction is equals to 0 because it is the case of the free expansion. There is no reaction forces on the three faces which are the mutually perpendicular to each other. So in this case, we can conclude that the volumetric strain is given by the del V by V is equals to strain in X direction plus strain in Y direction plus strain in Z direction. So which is equals to the 3 alpha T. From here we can see that the when we will find the thermal strain in the Y direction, it will be the alpha TB upon B, which is equals to alpha T. So all of the strain in all of the three direction summation is called as the volumetric strain. Note this point, the very important, and there is a material which is called the INVAR, which is the combination which is made up of the steel plus nickel alloy. Its alpha thermal coefficient of expansion value is equals to 1.2 into 10 to the power 6 minus 6 degree per degree centigrade. The interesting thing is that this material is used to maintain the dimensional accuracy, stability in presence of the temperature change. If in any of the beam there is a temperature change and we are required to maintain the dimensional stability, then we will use the INVAR material. So here are some of the example which you will find that the relation between the thermal coefficient of expansion value. So the alpha value of the diamond is less than alpha value of the INVAR, is less than alpha value of the steel, is less than alpha value of the copper, is less than the alpha value of the brass or bronze, is less than the alpha value of the aluminium. This is the relation between the alpha value among the different type of the material. So now we are moving to the case number thermal stresses. Now moving to the case number second. First we will discuss the variation of change in length due to the temperature change phenomena. Okay, so let's take an example. Here is the bar of the length L, and take the one strip of the dx at a distance of x. Its cross section is the x, y and z direction. Okay, so here I am taking the change in strain due to the different type of the temperature phenomena. First of all, I am taking the change in temperature is uniform. The second case, the change in temperature is the linear. Change in temperature is linear, which is given by the Tx by L, which is where the x is the distance x from the right hand side. The third case is when there is a temperature variation, which is this type of the parabolic, then the temperature at any section is given by the Tx square upon L square, and due to this the change in length will be different for the different type of the temperature phenomena. So in the first case, the change in length is equals to alpha integration of 0 to L T dx, which is equals to alpha TL. In the second case, when there is a linear change in temperature, change in length is given by the alpha integration of 0 to L Tx by L temperature change into dx, which is equals to the alpha TL by 2. In the case of the parabolic change variation in the temperature, the change in length is given by the alpha 0 to L Tx square upon L square into dx is equals to alpha TL by 3. From here we can see that in all of the cases the value of alpha TL is constant. Alpha TL is same for all the cases. There is only variation is there is divided by 1, there is divided by 2, and there is a divided by 3. So we can generalize this case. Change in length for when there is a temperature variation can be given by the 1 upon K alpha TL, and here K is equals to 1, 2 and 3. 1 for the uniform, 2 for the linear, and 3 for the parabolic change in parabolic temperature change or variation. Now we are moving to the case number 2 when there is a complete restricted expansion. Completely restricted expansion, case number 2. Case number 2 when there is complete restricted expansion is taking place. So in this situation, a bar which is fixed between the two rigid walls, and there is the material having the Young modulus of elasticity E, and the coefficient of thermal expansion is alpha, and there is a temperature change of del T, and this beam is the prismatic. So in this case total change is given, the strain energy in the y direction, because in the x direction there is no strain, and though there is no change in length, so it will expand in the y direction. So strain in y direction is given by the total strain in the z direction is equals to, due to the thermal load and strain due to the the strain due to the thermal effect and the strain due to the lateral strain in the lateral direction. So the total strain is given by the alpha T plus, in the lateral direction strain is given by the minus mu into strain in the longitudinal direction, which is equals to alpha T plus minus of mu into longitudinal strain is given by the minus alpha T. So the strain energy, the strain, not a strain energy, the strain, lateral strain is given by the alpha T into 1 plus mu when there is a complete restriction. In case of the prismatic beam, the formula can be directly used for the thermal stresses. For the thermal stresses, as we have discussed the thermal stresses. Here I am taking the generalized formula sigma thermal is equals to 1 by K into alpha Te. This is the formula for the thermal stresses in the material when the beam is the prismatic beam and made up of the same material, and this complete restriction or expansion in the one direction. So here K is equals to 1 for the uniform temperature change, K is equals to 2 for the linear temperature change, and K equals to 3 for the parabolic temperature change. So in all of the three cases we have discussed how to find the thermal stresses. So learn this generalized formula and you will find all of the cases. Now moving to the next case, which is called the case number 3. The case number third. The case number third, when there is a partially restricted expansion in one direction, there is a beam of the length L and the material having the Young modulus of elasticity E and the thermal coefficient of expansion is the alpha, and there is some gap between them in one direction. So it can be expand up to the lambda. If the expansion is less than the lambda, then there will be no stresses at the B point. But due to the thermal load or thermal temperature change, thermal stresses is greater. Change in length is greater than the lambda. Then there will definitely a reaction force will develop. So lambda is so we can conclude from here that if the change in length is less than lambda, then the reaction force will equals to 0. But change in length is greater than lambda, then reaction forces at B point, not A point, at B point definitely not equals to 0. There will be some reaction forces. So in case of partially restricted expansion, the thermal stress is given by the E into longitudinal strain is equals to alpha TL minus lambda upon L into E. So you can use this formula for any of the case smartly. So if the case of the partially restricted, use this formula. If lambda is equals to 0, then it is the case of the complete restricted expansion, and if lambda is equals to alpha TL, then it is the case of the free expansion. So from this formula you can learn all of the three cases which we have discussed. So now we are taking in one example how to find the value of the different. If the question is given on this if the question is given for the partially restricted expansion, then how to solve it. And this is the length of the bar and there is a gap between them which is equals to lambda. So if the mechanical stresses is not given in the question, then use this step. अगर mechanical stress नहीं दे रखी then अपन को इस step को follow करना होगा यहाँ पे. So first one is the strain. डायरेक्टली स्ट्रेस जो आएंगी वो क्या हो जाएंगी, इक्वल्स टू द गैप है. तो PL बाय फर्स्ट ऑफ ऑल टेकिंग द स्ट्रेस, द चेंज इन लेंथ और वी कैन से द स्ट्रेन डायरेक्टली इज इक्वल्स टू गैप और फाइंड द वैल्यू ऑफ द P. Then use this force to calculate the mechanical stresses, load by area. And the third step, find the thermal stress by the formula alpha TE. And the third one is the total stress will be given by the sigma axial plus sigma thermal. So if in the question the load is not given, then first step is to use this equation to find the load, and if the load is if the load is calculated, then we can find the axial load, axial stresses and thermal stresses by this formula, and the sum of this of two will give the total stresses on the beam. The next case is when there is a tapered beam. When there is a tapered beam held between the support and there is a temperature increase, in that case the stresses is given by here is the beam which is in the taper form. Here diameter is the D1, here diameter is the D2, length of the bar is the L, and there is a temperature change of 40 degrees centigrade. There is an increase in temperature. So the first one, the change in length total is given by the thermal plus direct stresses due to the direct load or axial load, which is equals to 0. So from here we can calculate the reaction forces which is acting at the fixed point. So thermal stresses is given by the alpha TL plus due to the axial load, the change in length is given by the strain is given by the 4RL upon pi d1 d2 into E, which is equals to 0. From here we can calculate the reaction forces R, which is equals to alpha TL pi d1 d2 by 4. That is the reaction forces in case of the taper beam when there is a complete restriction. The second one is the thermal stresses. Maximum stress is given by the axial stresses is equals to alpha TE into D larger upon D smaller. From this formula you can calculate the maximum stresses in case of the conical bar, which is given by the alpha TE into D larger upon D smaller. The third one is if you are required to find the ratio of the maximum stresses and minimum stresses in the conical bar, then it will equal to the ratio of the square root of D larger upon D smaller whole square. From this formula you can calculate the stresses, maximum ratio of the maximum and the minimum stresses in the beam. Now the next case and the final one, the case when there is a expansion for the thermal, there is an expression for the sigma thermal and delta of the spring or deflection in the spring. Just take an example here. A beam of the length L is expanding due to the temperature change, which is connected to the spring. And a spring is having the spring constant K. So the thermal stress in case of a beam is connected to the spring is given by the alpha TE upon 1 plus K of the bar upon K of the spring. So by using this formula you can find the thermal stresses in a beam when it is connected to the spring, which is given by the alpha TE upon 1 plus K of the bar upon K of the spring, and that is the K of the bar. So guys, it's all about the overview of the thermal stresses in the different type of the beam, which is in a square, non-square, rectangular bar. When there is we have discussed the different cases like that, the complete restriction, partially restriction, and there is a free expansion, and when there is a spring is connected to the beam, then what is the thermal stresses for that case. So this is all about the thermal stresses. Thank you guys, and for more video subscribe our channel. Thank you.